Okay, I first wanted also to thank Yves for inviting me to give this talk in this outstanding place. And just after thanking him, I was started to wonder why did he ask me to give this talk. And so I will try to find an answer. And I hope it won't be too old-fashioned after the wonderful talk by Peter about natural materials. And so I was starting to ask myself, what do you do when you find a hole in material space? And so maybe the first answer is go and find Yves and look if he hasn't filled it, because in many cases it might be the best solution. But I will try to show other strategies to do that. And so actually, maybe he didn't expect me to talk about that, but I want to talk about ways for microstructures to organize and architecture the materials, but more how to fill space in or gaps in materials science or material space by combinatorial strategies, and notably by using diffusion couples. And so obviously, if you want to make a new alloy, it's you try to fill a gap in material space, or you wouldn't do a new alloy, you would just redo an existing one. And so there, what I will try to show today is how to do that in optimized and affordable way. And it will mostly be using data from the literature, because I haven't been working that much in this area. But I think it's an emerging discipline that opens to the future. So if you look at some engineering alloys, modern engineering alloys for complex applications, they need to meet a lot of requirements, lots of functions, and usually this is achieved by very complex chemistries. So here I show three types of alloys: one aluminum, one steel, a stainless steel, and a superalloy used for an engine. And well, I won't go into the details about why each of these chemical elements added to the alloy, but each has a specific purpose, and you see that it can become extremely complicated. So, of course, to reach such compositions, to reach such chemistries, to make these alloys, it requires a lot of efforts of development. It's decades and decades of optimization of alloys, and usually it's done like that. You make different alloys of different compositions. So here I've restricted myself to 3 compositions because it's quite easier to show. If you're in a 10-dimensional space, composition space, it becomes awfully complicated and obviously untractable. And so this kind of strategy has many problems. The first is that it's very costly. If you talk to someone in industry, how do you make an alloy? How do you make an alloy development? He will tell you, well, if I need to cast a new composition, it's horribly, it's very, very costly, because a new composition, you don't exactly know how to process it. It's very complicated to make sure that when you want to make only one of the elements change out of such a composition, it's very complicated to make sure that the other ones are constant. And so showing effectively the effect of varying one composition is almost impossible. So it's difficult to be systematic, costly. It's difficult to get an optimization of the procedure. And how to tackle complex chemistry is an open question. On the other hand, people have thought, okay, so let's do that in a computer. And this is what's called now quite under the acronym ICME, Integrated Computational Materials Engineering. And this is, of course, a very good tool to tell you where to go and to give you hints or inspiration. And thanks to first robustness of ab initio methods, they have been developed a lot now. We know that they give reliable results, even in complicated case, multi-component chemistries and so on. From ab initio, you need to go upscale, up to the macro scale. We've seen that in the 2 previous talks that nature likes to subdivide architecture at different scales. So if you want to go to the atomic and macro scale, you have a lot to do. And it's true that upscaling methods are doing lots of progress. And also you need good models for microstructure properties relationships. But this is not the whole story. First, it's still very complicated in real life to have good models to deal with complex situations. Complex chemistries, non-isothermal heat treatments, coupling between plasticity and phase transformations, to name a few. There are many cases where it's very difficult to have good models. There are still remaining open questions in the field of nucleation to talk about phase transformations in metals, interface migration, and so on. Open questions tells you that the models may not be very reliable because you don't know what to put in them. So they may be phenomenological, but not much more. And then, of course, if you want to go from the atomic scale to the macro scale, including the properties, so not only the microstructure, this is still a very, very long and hazardous path, and you can get lost in the meantime. It's difficult not to get lost from here to here. So there is clearly a need for methodology in the real world, not in a computer, for alloy design that could go for affordable, so it should not be too costly to be able to develop new compositions, to test new ideas quite quickly, be systematic and optimized, so being able to be continuous in material space, and so able to fill holes, which is the topic of our talk today. So one of the methodology is to use, to make alloys with a continuous composition change. And this has been done for decades using diffusion couples, but not so much actually in the aim of designing alloys, but more by the thermodynamics community. And it's not enough to make a diffusion couple, but you need to have appropriate characterization and modeling tools if you want to translate this composition profile you've made into a real interesting tool for alloy design and understanding the effect of chemistry on properties and microstructures. So just a couple of examples of the traditional way to use diffusion couples or diffusion multiples, because this is much more than a couple. By the way, if you're interested in the subject, a lot of the examples I will give today are given from this review paper in 2006, which is really very interesting. So it's a review paper on all the combinatorial strategies for material science. So here you make this tiny piece here is a diffusion multiple made by different materials put together. And so you've got different precious metals. And the aim here was to define the different cuts into the ternary phase diagrams. And so for each of these boundaries, you look at the different phases, chemistries, and you're able to design for your instant here between chromium, ruthenium, and platinum, the different phases that form and make the ternary phase diagram of this part. And here you've got lots of them, and you get lots of thermodynamic data. So this has been classically used for ages. And also, you can use diffusion couples to get diffusion data, to make diffusion databases. So here, if you look at a profile between two miscible phases, then you can get, after heat treatment, the diffusion length. And if you have a good diffusion model, you can enrich diffusivity database. So these are classical use. Now, if you want to go a bit further and go to alloy design, you need a bit more than just making this, just taking a picture, looking at the phases and their composition. You need to observe really the microstructure or the features of the microstructures that you're interested in terms of properties. So which can be quite various depending on the properties you're looking at. And usually it's also multi-scale, the microstructures you're interested in, from the grain scale or phases to the nanometer scale if you have precipitates, dislocations, and so on. And what is quite important and is an avenue for future work mostly because it hasn't been done much is to get not only the final state of your continuous chemistry space, but also the kinetic path. So if you have your continuous composition and then you subject it to the heat treatments that you're interested in for your alloy processing, what is the kinetic path as a function of composition? So getting not only the spatial resolution of the characterization microstructure, but also the kinetic path to get from the continuous microstructure to the final microstructure. And then, of course, you need to characterize also the microstructure properties relationship. And this may be a challenge also if you have a continuous set of chemistries. How do you get the continuous set of related properties? So this is not always possible, but you may be interested in strengths, which can be quite easily done by hardness, for instance. But there are still to be devised some ways to test in continuous chemistries some more complex mechanical properties, I think. And then you may be interested in functional properties such as corrosion, magnetic, dilatation, and so on. So of course, if you want to look at corrosion, for instance, it's easy because you can look at the corrosion as a function of distance on a composition gradient, but then you might have interaction between different places and anodic couples and so on that make the understanding of the effect of chemistry much more complicated. So there is still, I think, a lot of challenges on such composition gradients to determine the set of properties. So first, I will show you a set of case studies mostly from the literature, a few from our work. But before that, I want to tell you to discuss a little bit how to make a good diffusion couple, and this is a kind of challenge sometimes, depending what you want to do afterwards. So if you want to make a composition gradient between two alloys of different composition, you need usually to stay in the solid state. Because if you go to a liquid state, then of course the diffusion distance will be large, which is nice if you want to have a large composition gradient. But you will have usually not a nice planar evolution of composition, but you will have a solidification structure with some segregation and so on. So usually it's better to stay in the solid state, and then it becomes a challenge to get the right diffusion scale that you want in terms of your characterization tools. Then it's good, well, it's not always possible, but it's good usually to promote metal-metal bonding between the two alloys and not to have the interface, which is usually not always of very good quality with oxides and so on, because it's better for interdiffusion. And then if you want to do some mechanical loading of your diffusion couple, it makes things much easier. You can roll it to get a longer diffusion distance. You can test it and so on. And that is not always possible, depending on the methodology and the alloys that you're looking at. So first, an example of, in many cases, you can get away with just simple metal-metal bonding at high temperature annealing. So this was a study on steels. I'll show why they looked at the effect of niobium on iron later on in my case studies. So here it was just bonding ultra-high purity of iron with some niobium. And so there is a layer here, and then you just keep it at high temperature for a while, 1450 degrees for 20 minutes, and then you have a nice diffusion couple with your niobium composition ranging from 0 to 0.1%. And then you can look at the effect of niobium on microstructure. So if you want to go a bit further, you can look at solid-state welding techniques. And this is maybe a bit... We'll learn probably more of this kind of techniques during the talk of Otsimar, who has been very much involved in these welding strategies. So you have now quite a lot of them. Friction stir welding is probably the most well-known. But you have linear friction welding, inertia friction welding, which are alternatives. So basically the aim is to mix two alloys together in the solid state, but at sufficiently high temperatures so that the materials are very ductile. And then you mix them together to make a metallic bond, and you get away from the oxide interface. So if you do that, you can do that between two identical compositions, and that's the classical way of welding. But you can do that with dissimilar alloys and then get a diffusion couple, basically, that you can heat treat later on. I haven't personally worked on that, but if you look in the literature, you see that it's not so easy to control precisely the distribution of chemistry in between the two metals. So the advantage of this kind of process is that it's very robust, very easy to perform, and now quite widespread. But it makes you a gradient between the two alloys, which is quite complicated. And depending on the process parameters, you can actually not mix the two alloys in the way you want it. So this is This can probably be used, but it's not so easy. Inertia friction welding is, I'll do like Peter, I'll use my arms, and it's basically with two pieces which have a cylindrical symmetry. You take one, you hold it very tightly, you rotate the other one at very high speed, and then you just crunch them together. And when you crunch them together, due to the inertia of the rotation, you have friction. Friction makes heat. Heat makes the material flow under the pressure. And then you get rid of the oxide layer on the outside, and you have a metallic bond. This is used quite a lot in super alloys. An alternative of this, which is almost similar in the concept, but it's not rotating, it's linear friction welding, where you have two components, one in front of the other, and then you push them together with an axial force, and then you have an oscillation between the two. The linear motion makes friction makes heat, pressure makes flow, and then you get rid of the material in between, and you have a metallic bond. So you see that you need to grip the two materials quite massively. Here you have the two samples, which are very tiny, and you can actually weld two materials like that, and it's used quite a lot in titanium, I think. So if you do that, you see, you get some very nice views. You get rid of the oxide on the outside, and then you just have to machine the outside, and you are left with a perfect bond, metallic bond. You have no oxide left at the interface, and on either side you have two alloys of different compositions. Here it was an aluminum alloy and aluminum with a metallic matrix composite on the other side. And so basically you have your two metals bonded with a metallic bond in between in the solid state, which is very good, I think, for studying diffusion couples. So we've actually done that on some aluminum copper lithium alloys for aerospace applications. And in this case, we're trying to do alloy design, actually. And in these alloys, precipitation is depending on the magnesium content as a minor solute element. And we're trying to vary the magnesium content to study the effect on precipitation. And so we've been doing this linear friction welding. And so we have one material on one side, the other one on the other side. The interface here, where the grains are deformed, but there is no aluminum oxide in between. It's been all removed. And it's possible to roll 90% of the material, and it will have it has a ductility as if it was only one composition. And of course, once you've welded it, the composition gradient is a step function, because you have only solid state welding at relatively low temperature, and you have no diffusion, no significant diffusion. But later on, you can make the diffusion as much as you want and get the diffusion couple at the scale you need for further characterization. So there are still many other processes, but one that seems to be developing quite a lot, and maybe Damien Fabreg will talk about it, I don't know, is spark plasma sintering. And spark plasma sintering is a plasma-enhanced sintering technique, where with a pulsed current you can increase very much the sintering kinetics. And if you do that you can do that on bulk materials and get a solid state bonding with diffusion lengths which are much larger than what you would expect from standard diffusion. In this way, some people have been joining, for instance, iron and titanium. And then you see that when you're in a multi-component system, here carbon, titanium, iron, you might have some strange things happening at the interface, because of course when more than one element diffuses, then the diffusion is not linear. You don't have, or not even monotonous. So if in this case, this may not be a very good case for studying alloy design between two compositions. But on the principle, SPS, I think it's a very good tool for this kind of purpose. Okay. So now, as I said, it's not enough to make a good diffusion couple to study, to go to alloy design using continuous chemistry gradients. You need corresponding characterization methods. And first, what you need for characterization method is to be spatially resolved. If it's not spatially resolved, forget it. You're not going to be able to map the microstructure as a function of composition on your gradient. So of course there is a matching of scales here. If you have a characterization method which has a resolution of 1 millimeter, then you need to have a diffusion couple on the scale of 10 or 20 or 50 millimeters to get something reasonable. If your resolution is 10 nanometers, then you can have a much more reduced chemistry gradient. So of course, all microscopy, especially optical and SEM, can give you a continuous image of your microstructure, but only for quite large features. If you want to go to smaller features, then you can go to X-ray methods, X-ray diffraction and small X-ray scattering. I will give you some examples, which both have the advantage of giving you the resolution for the features you're looking at, so nanometer or micrometer, and being able to give you the resolution in terms of your diffusion couple. And if you want to look at mechanical behavior, you can do things like digital image correlation, which can give you a continuous image of your mechanical behavior as a function of position. But for some properties like fracture, fatigue, and so on, it seems much more complicated, of course. And in many cases, you can go away with discontinuous measurements and not continuous ones. Of course, hardness is the most classical one. You could do calorimetry, TEM, take samples one after the other, or even atom probe if you want to look at very specific chemical features. But it becomes increasingly tedious to make lots of samples in a chemical gradient, and maybe you lose in the way the interest of doing that, because if you have a very nice gradient and then you need to cut lots of samples inside to get the different microstructures, then it loses part of its beauty. And then as I said before, what you would really want to do is coupling the spatial resolution and the time resolution to get the kinetic path to the end microstructure. Okay, so a few examples now. So first, mapping. This one is about mapping mechanical properties, actually. And so here people did a ternary diffusion couple, well, triple, diffusion triple, between palladium, rhenium, and platinum. And then using a nano-indenter map, you can get some mechanical properties. And if you do nano-indentation, you get not only the modulus, but also not only the hardness, but also the modulus. And then you can start to make maps as a function of composition of, well, here hardness in orange and modulus in blue. And so, okay, this is the same data shown in a different way. And then you can see what are depending on the composition, what are the ranges of yield of Young's modulus that you find. And then you can map these kind of things. Okay, a similar case also, using indentation, of course, it's quite easy to get a semi-continuous mapping of chemistry space. And then here in molybdenum, iron, nickel, in different phases, gamma, mu here, you can get the hardness as a function of content of the composition. And you can see that, and the modulus also. So here, it's a semi-continuous characterization. But it gives you, if the spacing between the different hardness points that you get is small as compared to your chemistry gradient, then you get an almost continuous measurement. And you can optimize the properties that you're looking at here. It could be hardness. Now, my talk is more on microstructure. So I'll give a few examples on microstructures now. And so here it's an example take from Chris Hutchinson's work. The idea was to look at in steels as the effect of metallic additions to the austenite to ferrite transition, where you have actually the transition wants to differentiate the composition of carbon in austenite to ferrite, so it's mostly depending on the kinetics of the carbon partitioning between the two phases, which is very fast. And if you add an element X, which could be nickel, niobium, molybdenum, or whatever, manganese, then this element has a very slow diffusivity in iron, of course, much slower than that of carbon because it's not interstitial. And there is a compromise for the material to find between making the transformation at the speed of the diffusivity of carbon, which is fastest, and making the transformation at the diffusivity of the element you've added, which can be nickel here, for instance, which is slowest but most interesting in terms of thermodynamics. And so you've got a lot of different sets of thermodynamics conditions, some that maximize the driving force and some that maximize the speed of the interface. And depending on the nickel content, you can go from what's called parallel equilibrium to local equilibrium with partitioning or without partitioning. And these different thermodynamic conditions at the interface result in very different microstructures that you can observe. And so you want to know after which composition you go from one to the other. So to do that, you just have to make a diffusion couple with changing nickel content here and make some. So this is not continuous in terms of kinetic path. That would be desirable, but it was here. It's just a snapshot. So basically, you have your diffusion couple with varying nickel content here between 2.6 and 3.5 weight%. And then you heat treated it and for a certain time and quench it. What has been transformed in ferrite is in white. What was still austenite is in black because it's transformed in martensite. And then you can follow the effect of the nickel content on the kinetics of the transformation. And you can decide, depending on the microstructure that you could watch at a higher resolution with another tool, what was the boundary between the two thermodynamic conditions. So here it's typically microstructural control, alloy design, to know, okay, if you want a fast or slow kinetics of your transformation, you can put the chemistry either at 3.4 or 3.2% here. And with a tiny, this would have been quite difficult to show because the different alloys, because the difference in content here is quite small. So to do that with individual alloys is quite difficult. Another case about phase transformations, but only watched here through mechanical properties, is about aluminum alloys. So this is also work from Australians. Aluminum, copper, magnesium is the classical duralumin alloy that was that has been used for 100 years in the aerospace industry, and it has some funny clustering behavior that is called rapid hardening. Basically, if you quench it, it's very soft, and then it remains quite soft at room temperature. And then if you age it at the intermediate temperature between 150 to 200 degrees Celsius, some clusters form, and you get hardening almost to the peak strength in 1 or 2 minutes. And then it stays for 24 hours. From 1 minute to 24 hours, it stays at a given strength. And then you still have another hardening, maybe of 20% more, so also after 24 hours during a subsequent phase transformation. So basically, you have this clustering effect that gives most of the strength and happens extremely rapidly. And it was poorly understood what was the effect of chemistry on this effect. So what they did is to design diffusion couples between different compositions, different sets of compositions. So what they call low solute couples, medium solute couples, high solute couples in the magnesium copper corner of the phase diagram. And then to cut these different composition ranges of the copper-rich phases, magnesium-rich phases, and so on. And then I won't detail all, but this is the kind of data you get after. Well, let's take one example here. Magnesium is constant. Copper here in triangles is evolving between 0 and 2%. This is as quench hardness, so it's quite soft. It increases as a function of the concentration in copper. And then this is after rapid hardening, so it's 5 minutes at 150 degrees, I believe. And then you've got, on the soft side, you have no rapid hardening, so the hardness stays absolutely constant. On the hard part, you get a substantial hardening, and then you can study the effect of composition on this behavior. So, well, this is the kinds of things you can do. Another case that I really like, this one, because I think it was a nice imagination. It's mapping the shape memory effect. So the idea here was to look into the titanium nickel and titanium palladium system and the mixing between the two. So here they made a diffusion couple. So here titanium is constant, open symbols here, okay, and palladium is varying. So here it's two diffusion times to get the couple. So you get basically from pure titanium nickel to pure titanium palladium. And then to map the shape memory effect, you do indentations, and then you do a heat treatment. And during the heat treatment, if you have the shape memory effect, the indentation disappears. And so if you map the indentation before and after heat treatment, you get the percentage of reversibility, and you get the shape memory effect. And this you can map as a function of composition. So here, what they did is to do this kind of reversibility as a function of temperature of heat treatment to see what was the temperature at which you get the shape memory effect. And then you can get a map of reversibility, so of the properties you look at, which is shape memory effect, as a function of the palladium content and as a function of temperature here in the y-axis. So I found this quite a very nice example of what you can do to do your alloy design. If you're looking at a given set of shape memory effect, you can design the composition and the temperature that you will get. A small example on precipitation. So this, I think, is a kind of a bit complex system to do, because when you start to diffuse several elements together, so to have two alloys with very different composition, then, well, if you're unlucky, you can get a complex diffusion path in between the two. So in this case, it was not too bad. So the composition was between basically pure iron on this side, well, with a little bit of nickel and aluminum, and iron, nickel, aluminum on the other side. And so you get a diffusion couple, and then you can heat treat it and get all the sorts of microstructure as a function here of position, so of composition in the chemical gradient, and here as a function of heat treatment time. And then you can map very beautifully the kind of microstructures. We could say maybe they're architecture, but this is not my point here. And see that for different times and compositions, you get a deep percolation and you get some alignments and so on. And then you can select, of course, some compositions and get into more detail about how the compositions suit your requirements. And well, and then you can even quantify these microstructures to get really the evolution for different aging times of the precipitate microstructures. So coming back to the example I showed you first to how to make diffusion couples, I'm coming back to this case where they looked at the effect of niobium on iron and made a diffusion couple. The aim here was to look at the coupling between solute and recrystallization. So the aim was to know how this addition of niobium changed the recrystallization behavior of the steel. And so the idea was to get rid of other effects and particularly not get rid of carbon, because carbon likes a lot niobium, and then you get precipitation and it becomes more complicated. So in order to look at recrystallization, of course, you need to make a diffusion couple, but then you need to deform it, because if you don't deform it, then you can't recrystallize. And that's one of the points I was making. Making a diffusion couple, if it's brittle at the interface, it's not good, because then you can't study anything that's related to deformation. And recrystallization is one of the points that you would need to have your diffusion couple deformable. So here they managed to deform it by inserting it into different pieces and rolling it. And then you've got a rolled diffusion couple with a diffusion profile, which is symmetric here because you had a layer of high solute alloy in between two pure alloys. So that was not sufficient to have this diffusion couple. They wanted to have another variable, and the other variable was temperature. So in order to have the other variable, they took their rolled diffusion couple, which is now a small sheet of steel, and they put it in a thermomechanical machine that was able to have a different temperature on either side. And so on one side you had 850 degrees, and on the other side room temperature. And then you had the thermal gradient in between the two. And so now, on this sample, you have on the y-axis here a chemical concentration profile, and on the x-axis a temperature profile, and you can look at how things go in terms of recrystallization. And then, okay, you look at that in the SEM, and you find a map. So here in y-axis you have the niobium content. So on the top it's 0, on the bottom it's 0.1. On the x-axis you have the temperature. So here you have 400, and here you have 900 or 850. And then you've got a map of the effect of composition and temperature. Well, the third axis would have been deformation, but it might have been a bit complicated to do. And then you can compare the boundaries, recrystallized, non-recrystallized, with some modeling. And here it's a model that was able to reproduce the shape of the boundary. So this allows you to do some microstructural control by varying here solute and temperature. Okay, this may be a bit coming back to determining phase diagrams, but just to show the possibility using X-ray diffraction to map the space of phase structures obtained by diffusion couples. And so here it was a triangle thickness gradient of chromium, iron, nickel deposited by PVD. And then, so it's almost a nice triangle. This is the experimental composition space. And then these people did some specially resolved X-ray diffraction with the synchrotron to determine on each point what was the phase. And this allows you to tell you which are the points which have that have a different crystal structure, BCC, FCC, sigma, and so on. So this is quite a powerful tool to characterize your phases in diffusion couples. I was talking about the different tuning your characterization tool to the scale of your composition gradient. And in some cases, of course, in cases where the diffusion couple is maybe a millimeter or a centimeter long, you wouldn't be able to map this kind of microstructure by a tool like TEM. But in some cases, you can have if you have a high resolution method, you can have a high resolution diffusion couple. And so here, this was looking at the effect of including aluminum in titanium and aluminum. And so the way they did that is to take a TiAl crystal and put it in liquid aluminum at 1200 degrees Celsius. And then you have a diffusion, and you create a composition gradient of aluminum within titanium aluminide. And here you have if you restrict yourself to the relatively low aluminum concentration, then you can here have a very, very short distance diffusion couple. And then you can look in a single TEM foil if it's positioned in the right way, of course, which may be a problem, at the effect of this composition on the ordering of the crystal. So, of course, in this case, your ability to characterize the effect of composition on microstructure is restricted to very small scale microstructure because you have a small scale composition gradient that restricts you in terms of microstructure development. So, of course, if you wouldn't be able to look at recrystallization or grain size in these kind of materials, obviously. because the scale is too small. Now, going back to precipitation, wanted to show you some results, quite preliminary, but anyway, that allow you to reach also time resolution, both space and time resolution. So this is a model alloy. It's just copper cobalt bonded to copper. So on one side you've got copper, pure copper, the other side copper cobalt. Cobalt precipitates in copper, and then if you bond them, you have a continuous composition gradient. And then this continuous composition gradient, you can scan it continuously while heat treating the diffusion couple. And by small angle scattering, you can get all the precipitation characteristics. So here are the typical size of diffusion couple we get. So it's about 1 millimeter in distance. You've got a small beam of maybe 100 microns to scan that. So you've got maybe 10 composition points in between your two compositions. And you can look at the effect of composition on the precipitation kinetics in terms of volume fraction, size, number density. And you can match this with models and do alloy design using these kind of things. So here you get not only the spatial resolution of the end point, but also the kinetic path, which is quite interesting. Going towards the end of my talk, I wanted to give a few examples about functional materials, because this kind of combinatorial strategies for alloy design has been also quite a lot used for functional properties. And people have been mapping all sorts of things. For instance, people have been mapping thermal conductivity. And well, I don't know anything about this, so don't ask me questions, but they have ways to using femtosecond lasers, they can map the thermal conductivity with a very good resolution here. This is a map of the thermal conductivity, and you can match it with a SEM map quite precisely about the conductivity of the different phases. And then, using diffusion couples or diffusion multiples, then you can, for instance here, get a map of the thermal conductivity as a function of composition in a nickel-rhenium diffusion couple. And this, for instance, if you want to you could couple that with mapping of electrical resistivity if you want to make a thermoelectrical materials, for instance. People have been also mapping dielectric properties. So using something called the scanning evanescent microwave probe. I don't know how it works, but anyway, you can get the dielectric constant, a map of dielectric constant and loss tangent on and you can map that with I don't know exactly here the resolution, I didn't write it down, but here the people managed to map the effect in composition of barium titanate, strontium titanate and calcium titanate, and so have a continuous characterization of the functional properties as a function of composition of the crystals. And also you can map magnetic properties. So here, it's a diffusion couple between molybdenum, chromium, and cobalt. So get different phases here, but then you can look during magnetic force microscopy, NFM. You can watch the different magnetic domains, and then map the Curie temperature as a function of the composition here in chromium and molybdenum. So it's there are many things that you can map. Again, you have to match the resolution of your characterization technique to what you want to look at. So just a few concluding remarks. If you, as I said, if you want really to do microstructure-based alloy design, you need to characterize your microstructure. I've given you a few examples. So it's best if it's non-destructive. If you want to have a continuous description both in space and time, in situ, of course, and automatic analysis, because if you want to, if you need to characterize each image by hand, and you have thousands of them, because if you start to have a spatial and time resolution, it becomes, you get really a huge amount of data, and it's combinatorial data material science, so you get maybe 100 different compositions and 100,000 different times, so you have 100,000 different data. So it can get quite large, so you need absolutely to be able to have automatic analysis. And probably the X-ray methods are particularly well suited to that, because the size of the beam is of the micrometer to millimeter size scale, but the size of objects you're probing with these kind of methods are nanometer size. So it's particularly suited to study the microstructure at the nanometer scale, varying in space at the micrometer or to millimeter scale. And it's non-destructive and possible for in situ. So to my knowledge, it hasn't been XRD hasn't been used for this kind of purpose in diffusion couples or to look at this kind of effects. But definitely it's been used a lot in situ to look at phase transformations. So here, for instance, it's a case in titanium alloy, where you take an alloy, you look with high energy X-ray diffraction, and you can characterize the phase transformations here from alpha to beta phase as a function of temperature. So if you did that with sufficiently small beam on a diffusion gradient between two different titanium alloys of different oxygen content or whatever, then you would be able to determine very precisely in situ what is the effect of each component, each solute on the temperature of the alpha beta transformation and on the kinetics of the transformation during a heat treatment that you would devise. Now, in terms of smaller scale, a nanometer scale, you can do, well, we've been doing quite a lot in small angle scattering. So here it's some platelets in aluminum alloys. And these kind of platelets give rise to small angle scattering if you send a parallel beam to the sample. And the characteristics of these streaks are dependent on the geometry of the platelets. And here, well, these kind of platelets like to nucleate on dislocations. So if you introduce different levels of deformation, then you get the same thickness. They're all precisely between 1.2 and 1.3 nanometer in thickness, but different diameters because they are more or less numerous and grow to different sizes. And these, you can map that. So I haven't got an example of a composition gradient. It will come, but we don't have it yet with this kind of characterization techniques. But at least you can map it. And here it's not a composition gradient. It's just a heterogeneous microstructure after friction stir welding. And just to show you that, well, this is 3,000 points of measurements. This kind of things also has been done for natural materials quite a lot on bones and so on. And so you can map quite easily by taking a few thousand images the evolution of here the thickness. So you can see that during welding you have an increased thickness in a transition area, full dissolution of the precipitates, and with that you can explain the hardness. So this, of course, you could use, and we'll do that in the near future, to monitor continuously the evolution of microstructure as a function of composition in compositional gradient materials. So a small summary. I hope I've shown you that there is a wide application range of combinatorial material science, and with that you may be able to fill a few holes in material space. If you do that, it's good to link with people who are good in processing, because I think the processing of these materials is quite a critical step. Almost anything can be mapped, any property, well, except, as I said, properties that are scale dependent, such as fracture. And of course, you can fracture only one material, and look at the fracture in the compositional gradient is quite difficult, so this is a problem. But only few experimental techniques allow both for space and time resolution. So if you want to get in the fourth dimension in time, then there are very few analyses that can give you that. And I was a bit short in time to do the link with modeling, but of course, it's very nice to show this evolution of microstructure as a function of composition. But what you really want to do is to link with modeling and to use these experimental approaches also, not only as a direct tool for alloy design, but also as a validation tool for models, which models can then be put into optimization tools to really do the design step to the final alloy. With that, I thank you for your attention.